Hi all, I'm Heather Beadle, and today I'm going to be showing you how we can use the PCA analysis tool in AASPI to gain some further geologic insight into a channel system on the northwest side of the Gulf of Mexico. This is work that was done by my master's student, Jacob Mag. We're going to be looking on the very northwest side of the Gulf of Mexico, like I mentioned, just offshore of Texas, by the San Luis Pass area. This is high-resolution seismic data that was shot by Tip Meckel and his group at the Bureau of Economic Geology at UT Austin. What's interesting about this data is it's high-resolution 3D, so we've got very high resolution compared to normal conventional seismic surveys. But because of the shallow depth of this area, we didn't have access to any well data. So if we look at what the seismic data looks like, kind of shown in the background, in the black and white, we've got a cross-section of the seismic data. We can see the unconformities that I'll be looking at. We've got a salt diapier that we identified, had been identified by others, as well as some normal faults and a gas chimney. And if we look down on the bottom right-hand side of the screen, we can see a comparison between conventional 3D data and then the high-resolution 3D data that Tip Meckel had put together. And so we can notice that we're missing that very shallow data by the seafloor, and being lower resolution in the conventional 3D, we aren't going to see kind of the high frequency depositional sequences that we're interested in. So one of the things that Jake did is he spent a lot of time mapping out these three unconformities that we'll be focusing on. So you can see them mapped here. He identified them using traditional seismic stratigraphy methods, looking at the seismic facies where there's truncations, where you can see erosional features in all three of them. And so these are the ones that, for the next couple minutes, we're calling the upper unconformity, the middle unconformity, and the lower unconformity. And so one of the first things you can do with any seismic analysis is you can run a whole bunch of seismic attributes. And these are wonderful and they're great. And I love seismic attributes. That's what my group does. We do seismic attributes. But you end up oftentimes with a lot of them. And so trying to see all those different patterns at once and incorporate them in your geologic mind can be confusing. So one of the methods we like to use is methods that revolve around dimensionality reduction. And so this is where you have your seismic data, you've generated a bunch of attributes, kind of shown here. We've got, a bunch of geometric attributes, we've got a bunch of spectral attributes. They're all showing us, little hints and details about what's going on geologically. And then we've also got all those other ones that Kurt Marfert was like, oh, you should try running these too. So we may have dozens of attributes that we want to look at, but then consolidate into one image to help us interpret. And so we'll be using a method here called principal component analysis. And what this does is you can imagine, like if we're working in 3 dimensions, we've got 3 attributes. And so we've plotted all these XYZ points. And what we do is we break them down into the eigenvector, which represents kind of this axis, this yellow arrow that we're showing on the left of maximum variance in the data set. So it shows you the direction of which there is the greatest spread of variability. And so that's our first principal component. So if we have 3 attributes, we'll have 3 principal components. If we have 200 attributes, we'll have 200 principal components. But what these do is these principal components and eigenvectors kind of give us an idea of a mixture of the attributes kind of in that multidimensional space that then we could plot out in maps. Geologic maps. And so kind of, for example, some of the ways we've done this before is shown in this area of the Gulf of Mexico in a paper from 2009 where they had 85 different magnitude components. And so you could flip through them all, look at the different channels. We've used methods like RGB blending with spectral decomposition in a sense, where you could look at 3 of those components at once. But in this case, with dozens of attributes, we may want to look at more than just 3 dimensions, more than what we could plot in a red scale, green scale, and blue scale. And so kind of comparing that and those channels, here we've got the first 3 principal components. So these are a mixture of different attributes. So principal component the first principal component isn't just one attribute, but it's a mixture of them that tries to capture a lot of the variance. And then the second principal component is another mixture of the dozen attributes that you're using that highlights other aspects in the seismic data, and so forth and so on. Luckily, most of the valuable information to us as geologists is in those first couple of principal components. So kind of going back to our study area, here are the results for the upper, middle, and lower unconformity for our principal component analysis. And so here Jake analyzed the spectrally balanced amplitude, sweetness, valley shape, peak frequency, peak magnitude, all as different inputs into the PCA analysis. And what we notice, and we just see with our geologic mind's eye, is we see a lot of features really popping out at us. From crevice splays to mid-channel bars, we can see in green by that green arrow, perhaps some floodplains. We've got the main channel more clearly identified. And so if we focus on the middle unconformity for a few seconds, here we can start to tie some of the features that we see in that PCA analysis. We can look at them in cross-section to try to give us a little bit more lithologic information. So like in this case, I've got a crevice splay, and we can see that typical mounding that we would have if we've got more sand fill or sand facies in that channel. Whereas over here with this cross section on the right hand side, we've got that sagging, which is a little bit more typical of silt and mud facies at these very shallow depths. And so that's one way we can take these PCA analyses and give it some lithologic meaning, besides just seeing the patterns and the geomorphology of the channel features itself. And so that was just a quick demonstration of PCA analysis. Jake's whole thesis, a video of his master's thesis defense is up on our YouTube page and up on our AASPI webpage. We have a lot of sponsors, a lot of companies that help us out with access to their software and their data. And if you're interested in trying out AASPI or learning more about our research group, we're always looking for more sponsors that pretty much help support the students and pay their tuition and stipend. So you can shoot us an email at aaspi@ou.edu. Thanks so much.